I hope everyone is enjoying being back on site, enjoying the conversations on the hallways, enjoying the talks. I know I do, so I'm very excited to be here after 2 or 3 years of online presentations. So I'm hoping to, we're truly back to normal, and I'm hoping to see most of you at many more conferences soon. A few of you might not already know me. I spent almost all my career building tools for developers mostly. I worked for close to 17 years on Advanced Installer, and I've built client power tools to help with our workflow and the community at large, being an open source project. And recently I joined the Visual C++ team at Microsoft, again helping build tools, make the tools I use every day better. This presentation is meant as a starter for a conversation, and the concepts I'm going to introduce are just a teaser for more in-depth conversations, and I'm going to point to auxiliary resources for folks that want to drill down and learn more, both articles and other presentations from conferences. And I do plan to do follow-up presentations on these topics based on the engagement I see from this version, and I'm going to do sequels for sure. But don't worry, no cliffhangers. Just a fair warning, maybe some of the ideas here might feel too opinionated, and that's all right. It's intentional to stir up conversation and have people buy into the idea and come forth and start a discussion with me or between yourselves. So I'm going to quickly jump in and try to do the impossible for folks that are not comfortable with some or not familiar with some of the functional programming concepts. I'm going to try to do a quick intro in roughly 10 minutes or so. So bear with me. In case the title didn't give it away, this would be a presentation on using functional style, not necessarily about functional programming languages. So functional programming, what is it about? Well, there's a lot of concepts here, and some of them you referenced in the talk abstract, of course. We're not going to have time to go exhaustively through many of them, but we are going to identify a lot of these ideas, a lot of these programming concepts in the examples we're going to see, and appreciate the way they change how we structure and talk about code. But first, I want to highlight a paradox of programming in that I think this really is somewhat intense and for many folks, I think it's difficult to pinpoint the exact mismatch in intuition and comfort they have towards programming and how we structure programs. And this comes from this impedance mismatch between what we need to tell computers to do and how we structure thoughts as humans. And machines are very much into local reasoning, whereas humans, we tend to think in bigger terms, in terms of perspective, and we are goal-oriented as humans, whereas machines are interested about small increments or small operations that need to progress towards a task. And we are very much about the ideas, what the purpose, what we're trying to solve, and of course, machines only care about the details of the how we want to solve this. Of course, we have problems reasoning about complex systems because we have limited capacity of how many bits we can hold in memory at a particular time, how many concepts we can juggle around in a particular frame of mind. That's why we build diagrams. That's why we try to distill the complex so that we have fewer moving parts. And yes, we are error-prone, and we need help keeping that in check. And humans have developed a very efficient language to reason about issues and complex problems, and that language, whether you like it or not, it is mathematics and logic. And machines don't know anything about that. Machines care about particular instructions. And we've been kind of trained into this mindset, I'm guessing, out of schools or by just imbuing what we see in the community and in mainstream programming languages, we're imbued with trying to think like machines and trying to micromanage operations rather than think in logical units or mathematical abstractions. And we have to always stop and think about the semantics of the operations we're trying to implement, the meaning of the programs, think about local bits, about denotational semantics, how we can abstract a given concept, and then very concretely tell the machine how to model that, and then how we can lift the low-level operations results into something that is human interpretable. So what is functional programming? Functional programming is a style of programming in which the basic method of computation is function application to arguments and transformations of data. And the functional language is one that supports and encourages a functional style. And I'm going to stress that a bit in this presentation. My focus is not on convincing folks to switch to using functional programming languages. The idea is to identify good patterns and things that we can learn from such theoretical exercises and apply them concretely in our domain, in our programming languages, in our frameworks that we design, in our APIs. But we do need to address the elephant in the room, because I think most folks are thinking about this right from the start of the presentation. And again, it's not about learning some functional programming language. It's not about finding a mythical C++ successor language or completely transforming the programming language to be something else. The idea is to learn and see what idioms make our APIs more fluent, more natural to use, less error-prone, and what patterns help us build simpler, shorter programs with less moving parts. Just a small snippet to get the sentiment across. In your mainstream C-like syntax programming language, this would be a trivial low-level loop to sum up some integers, and the main computation instrument there is variable assignment, so mutation is the core idea. Whereas in a functional style, we would think in terms of what we're trying to accomplish, what is the function, and we always need an abstraction, a function that does this transformation. So function application would be at the core. We're going to see more examples. So if I were to sum up in just 2 words, the rift here in terms of mental model would be functional is about what we're trying to accomplish, whereas imperative methods, imperative styles of programming are about the details, about the how. Michael Feathers had a very nice summary contrasting object-oriented programming and FP. Object-oriented makes code understandable by encapsulating moving parts, and we all consider this the staple of object-oriented programming, encapsulation. And that helps us build more complex abstractions and relationships between objects. Whereas FP makes code understandable by minimizing the moving parts. So I think this is a good goal, to minimize the moving parts so that we can reason locally about code easily. Before we start, I always want to highlight the historical background, the importance of engineers that worked before us, and we stand on the shoulders of their work. And when we talk about new ideas, I think a lot of innovations that we identify with contemporary programming languages, be it C++ or C# or Swift or Rust or whatever, we tend to consider them modern features, modern additions. But I think the majority of them are older ideas that just gain new appreciation. Just a few persons I want to highlight here and breakthroughs. If we think about lambda calculus, this is all the way from 1930s, when Alonzo Church develops lambda calculus for a theory of functions, basically. In the 50s, John McCarthy develops Lisp. I think a few folks have heard of Lisp, at least in school, if not for modern incarnations of dialects. And this was the first functional language, of course, influenced by lambda calculus. But it still retains something we identify today as variable assignment. Later on, Peter Landin develops ISWIM, the first pure functional language, again, based on lambda calculus. And this one didn't have assignments. So purity is nowadays associated with functional style, and pure functional programming languages try to make the best of this and sell it as a corner feature. John Bacchus, I think most folks associate his name with Fortran or Algol. A few folks actually know that he developed FP, a functional language that emphasizes higher order functions. And we're going to see a lot of these examples today of higher order functions. In the 70s, Robin Milner develops ML, the first modern functional language which introduced another concept, type inference, that we love today in mainstream programming languages. And of course, polymorphic types. These are no longer news. In the 70s and 80s, David Turner develops a number of lazy programming languages, culminating with the Miranda system. So for the first time, we surface concepts as lazy evaluation in the way we compose programs and request computation. And of course, the beloved Haskell, which started as a standard discussion through the late 80s. And in the 90s, I think the cornerstone additions to the language most folks have heard about or associated with the name, type classes and monads, main innovations that landed in Haskell, mainly the work of Phil Wadler. More about him later. And of course, this got standardized in the early 2000s. So all this for Haskell. So if Haskell is so great Why hasn't it taken over the world? Well, I claim that it has, in a way, but not directly. It's not something that happened in terms of we all started programming in Haskell or in other mainstream programming languages. Yes, there are companies and projects that run on Haskell and mission-critical software. And yes, you can write high-performance software in functional programming languages. But the idea is that concepts that distilled for 80 years in academic research and in pure functional languages have surfaced in mainstream programming languages as if novel ideas. And we are trying to adapt them. Of course, not all of them fit in the context of imperative programming languages. We're still trying to figure out ways to make them feel natural or feel at home. If we're talking about C++ or if we're talking about Swift's algorithm library or Rust, each community, each niche, each mainstream programming language is trying to borrow concepts and make them feel at home and see how we can make code that we write feel simpler and more easy to reason about. So C++ has indeed become more functional from mundane concepts like lambdas that everyone is using these days, standard function, higher order functions, value types, constants that we're trying to use, lazy ranges, fold expressions, and even monads. Yes, there are monads in C++. A quick taste of Haskell. Can anyone figure out what this piece of code does? I'm going to try to demystify the syntax. So the plus plus just means list concatenation, and we have some list comprehensions that tell us that y's are all the x's that are smaller, that are greater than a, and z's are all the x's that are smaller than b. So what do you think this does? It's an algorithm. Quick sort, yeah. Quick sort, very good. So if I give them better names, I intentionally left them dry. So we would have a recursive application of the quicksort function to the partitions we construct using those list comprehensions. So if I were to have like a step-by-step modification of how these things happen, this would be the list cells that we're decomposing and sorting there. So the idea here is that we're declaring our intent in how we want to attack this problem. We're not describing the steps or the mutations or how we need to pivot. We're just expressing intent using list comprehensions and function application to say what we're trying to achieve in partitioning and sorting the sequence. So if we were to do this in a very imperative style, we would have to, don't try to read the code, it's not important. This was just pseudocode lifted from standard algorithm book by Corman. So immediately we see that we have lots of moving parts. We have complexity, we have to reason about state and boundary conditions, and it's very easy to screw it up. Anyone who's tried to implement a quick sort or a binary search or something that's very simple as an idea, but very difficult to get right in all the condition, all the details. And quick story here. In 1986, you know I love history bits by now. So in 1986, Donald Knuth was asked to implement a program for the programming Perls column in communications of ACM. And the task was to read a file of text, determine the n most frequently used words, and print out the top n with their respective frequencies in that body of text. Sounds like a standard interview problem or I don't know, school task. So, you know, Don Knuth is a pretty thorough person, pretty thorough programmer. So his solution, written in Haskell at that time, that was fashionable, was 10 pages long. And it was correct. It was a correct and thorough solution. But I want to highlight a different solution. How many folks have heard of Doug McElroy? Just one hand. So Doug McElroy was instrumental in the developer of Unix, and for a while he even managed Ken Thompson and the team that worked on on those projects. So I think we all love and appreciate a good pipe, and I think we have many Linux enthusiasts here. So he's the person that's responsible for this innovation, the pipe. And this is his solution to the very same problem. And this is a complete solution. So it's not 10 pages long. It's 6 lines of shell script that accomplishes the task, the very same task in finding the word frequencies and sorting and printing them out. I do encourage you to read more about Doug McElroy. I think he deserves more exposure and recognition for his contributions, and not just this script. So taking inspiration from Doug McElroy's Unix shell script, you can think about writing an algorithm in your favorite programming languages, doesn't have to be C++, and try to solve the same problem, but in the spirit of Doug McElroy's pipe, and see what you come up with. And how would we start on this journey? Well, it's all about functional programming, so I guess we should all read up a way thicker book than that one about category theory and endomorphisms and monads and all the crazy mathematical concepts required, right? There is actually a book like that, and I did enjoy reading it, but I wouldn't recommend starting with that one. By the way, I put a link there. It's in PDF format. It's freely available. If you want the printed version, there is a print order version. Very good book. But we have to think about how does this apply to our beloved language. How does this translate? How can we use this in C++? Is there value for us today from these concepts? Or is it just a mental exercise or something that we like to think about and write toy programs or academic papers? Can we use this in C++? And if there's a takeaway from this presentation, would be to start with this book. So if you want to learn more and see many more examples than I have today, I would recommend this as a starting point for your exploration, for your transformation, for helping you think differently in C++. Ivan is at this conference, by the way. You can find him on the hallways and ask more. I have to pick something because the time format doesn't allow me to go into detail about everything. So, okay, so apparently the stream is working now. We had some technical difficulties before. So I had to pick some topics, and my first choice was lifting. And it's gonna sound like it's something complicated, but I want to make it sound very pedestrian, very simple, and I'm going to show very concrete examples. And when we're talking about lifting, we have to talk about higher-order functions. And don't get scared about the name. Higher-order functions are everywhere. You are using them. If you're using the STL, if you're using the algorithms, if you're using ranges, you're using higher-order functions. If you're providing lambdas or predicates, you are using higher-order functions. yeah, I had to mention Boost high-order functions library, but I'm going to focus on another library, less known, called Lift by my friend Bjorn. And it's a C++ 17 library. Has simple context per high-order functions of predicates and helps us write and compose functions easily. And we're going to see how we can do that. The reason I chose this library is because I want to highlight the way it helps composition, and because it's an easy library to read and understand. The source code is right there. A few high-order functions that it provides, the usual suspects. I think they're pretty self-explanatory by the names. But let's see a concrete example. Suppose we have a structure with 2 fields, and we have some way of projecting those fields outside by selecting the name or the number in the structure. And we want to sort the elements, the structure elements, by name, by one of the fields. So instead of being very explicit about it and just sticking a lambda there and doing the usual thing, we can, I have to showcase the way we can compose things. So we're composing the less function and select name. And we're providing this as a higher-order function for the sort algorithm. Don't worry about the compose details later. And if we want to do find if, again, we're interested to finding something that it's where the employee number is equal to 5, whatever that means. And yes, we could have written a lambda and be very explicit and be very imperative in style in selecting what we care about there. But I wanted to highlight how we can compose these two functions and even have a partial function application by providing 5 there as an argument to equal, again, to accomplish these things. And don't worry, if you can use C++ 20 ranges, you can do things like this and more with projections. So it's already in the toolbox. You don't have to reach for some kind of third-party library. I just wanted to highlight it as an example. And don't worry about trying to parse this macro. It's not that important. I think the example here is much more interesting. And again, using Bjorn Faller's lift library here, we are trying to lift an overload set, so not just one function. So we're trying to lift an overload set of all the toString functions, and basically we can write a transform that could work on different kinds of input sequences. Here we have vector of integers, but they could be anything that can be toStringed and transform them in the destination collection, which would be a vector of strings. So again, we're seeing a way of lifting the domain of the function application. And again, I'm going to draw some diagrams to bring this point home. By the way, this would be the presentation by Bjorn Faller to watch. The link is there if you want to see more details and more examples. I'm going to come back to lifting in a bit. OK. Let me check on something. Yeah. But first, we're going to have to talk about boxes. So I picked another concept, and I need to talk about this so that we can digest the examples and see lifting in action. And that the other concept that it's deeply rooted in functional programming style is the idea of type constructors and a way to capture a value with its context. So in C++, we have a few type constructors that are already there in the box, pun intended. Unique pointer and share pointer, vector, optional, standard function, and many others. And for each of them, we have a way of poking the value inside. So we can get the value that the pointer points to. We can get an element from the vector. We can get the value from the optional, and so on. We can do the function application. But the idea here is that what we should aim for is not looking in the box. The idea is not checking at each step to see if the value we have in this container is actually valid, is actually usable at a particular stage in the pipeline of the computation. The idea is to chain multiple transformations, apply multiple functions, move the data around through the transformation pipeline with its context, and at each stage, by different techniques, and I'm going to highlight fmap as one such technique, we can apply the transformation based on the value in its context and move it further along without querying it at each stage. And only at the end, we query the result and see if we have a successful transformation. So standard optional is such a tool in C++ since 17. So to reiterate, don't use optional for error handling, because that would force you to check it if it has a value. And try to use optional to chain computations and build APIs that are intuitive and fluid in the way they compose. And of course, you can draw inspiration from programming languages that have gained this tool long ago. If you want to read more about functors, applicatives, and why not monads, there is a series of articles that I think explain the concepts in a very intuitive way using pictures, so no fancy mathematical explanations. The link is there. So I said to draw inspiration from Rust. In Rust, using the option type is pervasive. All APIs expose this as a vocabulary types, and developers are used to dealing with option types. And the idea here is, again, don't query the value within. Try to chain it, or try to do pattern matching to see if you match a value or not. The magic of applying the value should happen in a way that masks the client code from the value within. So we should think about doing the transformation to the context and putting the value back without actually looking at it to see if to query the value. And let's see some examples. Let's think about capitalizing a string, right? So we could have a capitalized function that takes a string and returns a string. And we can obtain this string from an API that can fail, and we might not get a string back. So we could model this as an optional string out of that API. And here we have the idea that I mentioned earlier. The code actually looks to see if it has a value. So that if actually checks. And if I got a value from the API, then I do the transformation I want to do. This is not the ideal workflow. And of course, we can change that to an optional string. But that's not the idea. The idea is building a lifting operation. And this is where I go back to lifting. We can think about a lifted capitalized function that works on an optional string and returns an optional string. So rather than going from string to string, it goes from optional string to optional string. It's like changing the domain and codomain of a function. So we hide these details inside this higher order function. And we can think about them in terms of raising or lifting the domain, lifting the abstraction. So if our capitalize works from string to string, lifted capitalize works from optional string to optional string. And yes, of course, we're not going to build sibling functions or duplicate all of our transformations to do this. This was just to get there. There are higher order functions that help do this lifting operation transparently. And one such possible implementation would be an fmap function, which takes as an argument a function from A to B. So standard function takes an argument of type A and returns a value of type B. And it does a transformation on an optional. So it transforms an optional of A into an optional of B. And it does so using any function. So this is a higher order function because it takes a function as an argument. So fmap is a higher order function. One of our first examples today. And lifted f, the exact same diagram, exact same idea, now just generalized. For an f function, we now have a lifted f through an fmap higher order function that now takes us from optional of A to optional of B instead of A to B. So instead of going to string, optional string to optional string, let's say. And if we want to express that concretely, let's say we have a two-stage transformation. So we have, we want to trim a string and then measure its length. Standard way of chaining these kinds of operation. So we want to trim the string, any white space and stuff like that, and then we want to see how long it is. So at each step, we might have a failure to produce the result. So trimming might not yield, let's say it might not yield a result, or length might fail. Of course, these are trivial examples, but I want to build an intuitive feel about this. So we have to raise the function application domain. Trim is from a string to a string, and length is from string to int, gives us, or size t or whatever, gives us the length of the string. And we can compose them using two fmap applications. The first lifting operation happens for trimming, and the second lifting operation happens for the length function. So don't worry about the syntax if you don't like it, it gets better. Another way of writing this, if you don't like the standard function route, and you have many reasons not to like the standard function route, you can write it this way. And again, this is a higher order function, another flavor for fmap, and not the only one, where you can take the function as the function that needs to be lifted as an argument, and again, it would lift it in the optional of type, domain, and codomain. Let's say we want to build a symbol table for a program we're debugging or something like that. And maybe we have an API that gives us an IP counter, a function address, currently executing function, let's say in a debugger or something like that. And we want to get the debug location from this, which might be the function name where we stopped, where we're breaking the debugger. So we might have an API that loads a symbol. So for a given program counter, gives us a symbol. And then we want to transform that symbol, which might be some internal structure that we represent in the debugger, into some presentable information to the user, like a string, friendly display string. So This would be that way of checking at every step. Do we have a current program counter? Could be an optional, could be unavailable. The API might have failed. Did we manage to load a symbol? Do we have a symbol? Yes, no, abort. What do we do? We return an empty optional. And then if everything went OK, we're trying to display the string. So reorganizing our thoughts here, we're trying to, again, compose by lifting those functions and doing fmap. So the inner fmap helps us map the loaded symbol. So helps us going from the current program counter through the load symbol function, which is the lower function, and then gives us an optional symbol type, whatever the symbol type is in our system, doesn't matter. It gives us an optional of that type, but we don't look at the optional. We don't care at this stage if that succeeded or not. And then we compose, we take this further, and we lift it using another fmap transformation, and we're applying toString to it. Let's say we have an overload of toString for that particular debugger structure we're dealing with. So, and at the end, we're yielding an optional string. So that's the intended result. The goal was to display a string of that function name where the debugger stopped. So at the very end, we get an optional, so we get that box, and it has a context. And at the very end, we open the box and see, OK, do we have a function name there to display or not? And you can do fancier things if you care about syntactic Ciura. We can do the same thing with a vector. Don't think this is tied to optional. So the same pattern can be applied to any type of such box. And I mentioned a few earlier. So vector would be another prime suspect here. For example, we can have an fmap function, again, from A to B as a function application domain. And inside, we can use another higher order function from the standard library this time, standard transform. Standard transform is a higher order function. Proof, it has an argument, which is a function. So our fmap uses standard transform to transform a vector, to transform from A to B. Our function is A to B, and we're trying to build a new function that goes from vector of A to vector of B. So we're lifting the function into a new context, which is a collection of A's and B's. So let's see something like this. Again, we're having the length function for string, and now we want to operate on vector string and produce a vector of integers, or size t, if you want to be a purist. So we could traverse the vector of strings and apply length to each element and then insert it in the vector of integers, of course. But we can imagine this might be a more complicated thing where that length operation might not succeed, or whatever API we're talking about. So again, a way to compose this using our fmap lifting mechanism from the previous slide. We can fmap from string to int and use the length function, and now we get a new higher order function. So we have a lifted length function that we apply to the names vector. So the input for this transformation is the vector of string, the names, and the lifted function, the lifted length function, which now operates on this vector, but yields a completely new type of box, a box of integers, which represents the individual lengths of the items there. So we've seen a few concepts. We've seen the type constructor, and we had two examples with optional and vector. And this helps create a box that wraps another types. So an optional wraps the type within it. A vector wraps, models a collection, more than one value. So a box can hold more than one value, by the way. So a vector wraps a value of its type, let's say integer, strings, whatever. And the idea of the context is essential here, because it encapsulates the types, and it can carry context along the processing pipeline that we build. And we've seen functional lifting, and that was a way of creating a higher-order function, like we showed with fmap. And it helped us create a new function. Instead of going from A to B, that mechanism helped us build a new function that goes from box of A to box of B, where box was optional, vector, or whatever, shared pointer if you want. So at any step, we try not to break encapsulation. So we try not to query the value until the very end. And it helped us build composition. Instead of writing a bunch of if-else branches and structure our code by nesting conditionals and multiple exit points from the function and dealing with all the conditionals, we're trying to build a pipeline, something in the style of repeated function application, and at the very end, we see if the pipeline succeeded or not. And we have monadic extensions to standard optional since C++23, and you can even use them earlier if you don't have access to fancy C++ versions. There are many implementations of monadic extensions freely available on GitHub. I would recommend the one by Cybrand. You can find it at tartanllama, GitHub/tartanllama, and look for optional. So let's say we have a string view to int function here, where we're trying to do a type conversion, and we're getting a buffer, and we're trying to convert it to integer if we can. And inside, we're using the from chars API. Don't worry about the error handling and the details there, not important. What I care about is the processing pipeline. So instead of building a function that deals with all the error conditions and tries to figure out, okay, what are we doing, what are we returning at each stage when we failed to transform the input buffer into a string, we're building a linear sequence. So instead of nesting a bunch of ifs, or worse, building some callbacks. So instead of nesting, we want to build a linear stream, so something that feels like steps that we proceed through. So this is where the and then, or transform, or else functions from standard optional can help. Don't mind the details. It's not important what each step actually does. Just an example. The main takeaway here is that we're building a transformation that looks linear. It's not about branching or nesting within. And at the very end, where we changed a bunch of things that all had optional things in them, at the very end, we do the dot value, and we see if we got something out of it or not. More on, and I think this is very close to what we can do in declarative style in C++. But I think this slide from Ben's presentation on declarative style in C++, I think that this is the slide that best synthesizes the presentation, but I do recommend you watch it. I put a link there. Is about what's the signature element. So the signature element would be function application and higher order functions and chaining and composition. This is what we want to target. So we want to stay clear, if possible, of statements and mutation and difficulties that come composing with such low-level bits. So what we have to remember is that expressions yield values. and statements do not. Might seem obvious, but we have to keep remembering that. The distinction between working with expressions and working with statements. That statements cannot function without mutation. I do recommend another presentation, and not because it's about a C++ successor language. It's because it's focused on values and value semantics. I don't believe it's yet on YouTube, but should be soon, from CPPCon this year. So look out for the values talk by Dave Abrahams. Very important. I think it's very important to watch it, even if you're not interested in an experimental language. More references for value semantics that I think might help once you get past the principles, and I hope I gave you a good teaser to stir up interest to explore more. I would recommend this presentation by Juan P. Bolivar Puente, Value Semantics, the Most Valuable Values. I love this presentation. And it's all about value-oriented design and how the talk actually tries to reconcile functional and procedural programming by focusing on value semantics. So that's the most valuable bit out of what we can translate easily in C++. C++ is very much a value-friendly programming language, but we have to learn to take advantage of this and distance ourselves, if possible, from 2000-style programming of using share pointers and object-oriented class hierarchies. So, like functional programming, it promotes local reasoning and composition. So that's why I think it's important to try to follow some of Juan P's examples there. And I think it's pragmatic, so definitely worth watching. Another presentation on values that I highly recommend, again from Juan P., Squaring the Circle, Value-Oriented Design in an Object-Oriented System. This one is about trying to bridge the gap and see a few techniques we can use to retrofit some of these value concepts and working in this different mindset in a code base that is heavily legacy, heavily object-oriented. If you want to learn more about immutable data structures, this is something that's another cornerstone of functional programming. I haven't touched immutable data structures at all in this presentation. They're way outside the scope. But if you want to learn more, this would be a good starter presentation, again, by Juan P. And of course, we've seen already, at this conference, we've seen a bunch of presentations on ranges, even some controversial bits. So I have to mention a few of the ideas of ranges, and they all stem from functional programming paradigms. Just a quick flavor, in case someone missed the train and not comfortable with C++ ranges, just a quick before and after shot in terms of, I want to highlight the style. Don't follow the details. They're not important. I want to get you a flavor for the style. So on the left, we have a very step-by-step, intentional, what you have to do computer to solve my problem. And on the right, something more kind to the goal we're trying to achieve, or the higher level transformations that we're trying to pipe through. So reversing, filtering, dropping elements, taking the first elements, filtering on a given predicate, and so on. Again, I think that the idea here, that's why I'm putting it side by side, is to contrast the how and the what we're trying to accomplish. I think we should try to stay closer to what we're trying to accomplish and be succinct, and there are less chances of erring out. Again, another example. Don't mind the details, just appreciate the differences. I think C++20 ruined one of my favorite interview questions, and that is to split a string. How many of you have gotten this interview question? No? A few hands. So this kind of thing becomes trivial now. Fair warning, I don't think any interviewer will accept this answer. They actually want to see the algorithm. Okay, so getting back to the pipelines and Doug McElroy's magical script, we can try to, I gave a teaser back a few slides back, we can try to do a similar thing in C++ using ranges. Don't try to decompose this in your head. I think you can intuitively gain appreciation of that this is very much close to what Doug had, at least as close as we can get with what we have as building blocks. So we can go get closer to that goal. We're never going to get the syntactic sugar and the succinctness of something like Haskell or shell script commands, but we can strive into that direction. For sure, we can have less moving parts and less ifs and simpler code. So this is what we should strive for. We've already heard a few gotchas from Nico in his keynote on ranges. I'm going to reiterate some of them that I consider important. And views, remember that views have reference semantics. So all the reference gotchas of C++ apply to views. It's nothing new. We have to just remember that they have reference semantics. As always with C++, const is shallow and doesn't propagate, as you might expect sometimes. So be aware of that. Some functions do caching. I put this deliberately in after Nico's keynote, just to raise awareness once again. Don't hold on to views, and don't try to reuse them. The safest is to use them ad hoc or as temporary values, let's say, like I had in my previous examples here. So use them ad hoc in line where you're doing the processing. Don't try to hold on to them. And if you really must hold on to them, if necessary, make copies so that, because they're cheap, and you avoid surprises due to caching and other bits. So I would close off by reminding you of Phil Wadler. We've seen him at the very beginning. And I'm going to draw inspiration here from Ivan again. This is how Ivan likes to close his talks, and channeling functional programming in C++, I have to close the same way. So listen to Phil Wadler, make your code readable, and pretend the next person who looks at your code is a psychopath, and they know where you live. So program so that you don't have any surprises. And with that, appears I'm on time. If you have any questions, feel free to ask. Or if we have questions online. If we run out of time, I can take questions off the record. One question on the record.
Oh, Victor, thank you. Thank you for the talk. So just one question. I'm someone who is going to try functional programming, who haven't tried yet. So I'm wondering how the debugging would be. Say, are the debuggers ready for functional programming, or is it something that we have to watch out for?
That's the most uncomfortable question I get when I give this talk. But I'm glad you did it. So I would say it's better than debugging macros, which is not much. The idea here is that when I tried to learn Haskell, this was the most difficult part for me. I tried to, at each step, I tried to see, okay, what am I transforming? Am I getting what I'm expecting in the new list? I try to, and it's even harder in a pure functional programming language because it's harder to output stuff, to see, to peek at the program. So first of all, having less moving parts means you do less debugging. You need less debugging. Because the parts you're composing can be individually tested if you want them. The beauty of, if possible, if you're trying to program in a pure style where the input is processed and it gives an output without mutating external state, is the beauty of that is that you can rip the parts, the parts, and each one can be individually tested because it has no dependency of any external state. It just has an input and an output. So this eases up when you have a chain of transformation. You can take out parts of the transformation, and this is what I do. Take out parts of the transformation and see if is this working. Okay, this is working as expected. I put it back. Then take another part of the transformation. Is this working now? Put it back. So because you have an input and an output, and if possible, you don't modify any external state, you don't have any side effects, then it's easy to take bits and test them in isolation. It's even easier to mock functionality if you want to do tests, automated tests and stuff. So first, it eliminates the need to inspect variables and watch for memory transformations. And second, it's easier to test in isolation.
Thank you.
But there is no debugger support, like magic. I think we have to close the stream here, but I can answer questions off the record. So go ahead. You can ask the question.
Okay, thanks for the talk. I pretty much enjoy functional programming, and I try to incorporate it in my C++ code as well. But I always wonder whether, what are your experiences with performance implications if you change the style to this, right?
You have to do it responsibly. So not everything is going to magically be fast. So, but I think this applies in general to C++. You can really surprise yourself by copying stuff you didn't intend in C++ without trying to do functional transformations. So you have to be careful at each step. If you have concerns about ranges, ranges are lazy, so most of the time. So you can try to be eager about evaluating at certain stages, but in general, they try to be very efficient. So if your concerns are about ranges, I would say 90% of the time you shouldn't worry about that. They are performant. They cost in terms of compilation time, but at runtime they basically boil down to almost nothing. So it's like inline functions. All that type traits and boilerplate will just go away when optimized. But yes, you can do unoptimal stuff. You can copy things without meaning to. There are perils around the optional constructor, for example. If we talk concretely about optional, and I have one more presentation tomorrow where I give an example where optional can bite you if you don't know what you're doing. So you can accidentally build and accidentally call copy constructors and do unnecessary things. But I think that's not necessarily a problem of working in a functional style. It's a problem of not knowing what you're doing in C++ in general. Like the regular C++ foot guns apply to functional programming as well. So it's not a guarantee that it will be optimal. But having less moving parts means there are fewer chances to get it wrong, in my opinion. I'm not claiming guaranteed optimal programs. Nobody can do that.
Sure. Thanks again. Yeah, I have to benchmark more, I guess, if I'm using it. And now
always measure. Intuition fools you. Always measure. Yeah, always measure. If there are more, I don't see people lining up for the mic. If you have more questions, do catch me in the hallway or around. I'm easily identifiable.